So, welcome back to Calculus. We are continuing on in our study of the definite integral here from section 5.3. This is the second video for this section. So if you missed the first part, go back and watch it before you watch this one. All right. So we have one more definition, and then we actually get to start doing some problems. So that'll be a little bit more interesting. The definition says if y equal f of x is non-negative and integrable over the interval ab, then the area under the curve y equals f of x over ab is just the integral of f from a to b. In other words, our area is equal to the integral from a to b of f of x dx. Importantly, f of x has to be a non-negative function on this interval, okay? Because area is a positive concept. So it's only an area if it's positive, right? We don't have negative areas. Now, we're going to cheat just a little bit here shortly. And really, we're going to treat we'll treat the bits underneath the x-axis as negative areas. They're not technically areas, but we can kind of still think of them the same way. And so we'll see that here when we get into some of the examples, which are coming very, very quickly. All right, so as we head into finishing up this section here on the definite integral, we have a few basic integrals that we are going to be able to find using some formulas. And they're very straightforward, so I don't think, hopefully they won't be a problem for us. But here's our first one. The integral from a to b of c, where c is a constant, dx, is going to be equal to c, that constant, times b minus a. Again, b minus a is the length of our interval, right? It's the two endpoints of our interval just subtracted. And why does this work? Well, quite simply, since c is a constant, we just have a line that goes straight across our graph, which means it makes a rectangle. And how do you find the area of a rectangle? You do length times width. And so in this case, we have a length of b minus a, right? Whatever, if this is 7 and that's 2, 7 minus 2 would give us a length of 5. And then we have a width, or height, or whatever, here of c. And so it's just length times width, and there you go. It's just finding a rectangle. Our second one, and there will be a third one here in just a minute, when I have more space on the board, is a little bit more complicated. This one's going to use triangles, really basic triangles. So we have the integral from a to b of x dx. This is going to end up being equal to b squared over 2 minus a squared over 2. And here's why. We can think of it really as two different cases here. I guess I want that in this area, so I should shade that one in. Let's first say that a is negative and b is positive. In this case, we're going to get a triangle here, or you can see my two triangles. Now, one would be a positive area, and the other one would technically be a negative area. Again, it's not really an area, but kind of think of it that way. Well, this triangle has a base of b, because it goes from 0 to b, and it has a height of b because we're using the identity function x. So at b, it would have a value of b. And how do you find the area of a triangle? Base times height divided by 2. Well, b times b is b squared divided by 2. And then since this triangle is negative, there's my minus sign. And what is it? It's a times a squared, divided by 2. So it works really well for this example. But what if they're both on the same side? They're both positive. Well, now it's like taking the big triangle from 0 to b and up minus the small triangle from 0 to a and up. And it's going to work exactly the same way. The big triangle is going to have side b and a side b, giving me the b squared over 2. The little triangle will have sides a and a, so it'll be a squared over 2. And so it works. So anytime you have the integral of the identity function x, it's just b squared over 2 minus a squared over 2. All right, one more, and then we're almost done. I promise. Let me get more on the... All right, a couple more things real quick, and then I have one more example to do for you. Then this section will be done. So the first one is one more integral that we can evaluate using kind of a formula. The integral from a to b of x squared dx is going to be equal to b cubed over 3 minus a cubed over 3. And I'm not going to attempt to prove this one. Not yet. It'll certainly come back, I think, in the next section. And then we have an average value for a continuous function. So this would be if you thought about a function over an interval, where is its average, what y value is its average between a and b? And so turns out all we do is we take the area of the function by taking its integral, and it could, I suppose, technically be negative here, and that would be okay. We take the area, there's an integral from a to b of f of x dx, but then we multiply it by 1 over b minus a. Well, what is that? It's just taking the area and then dividing by the length of the interval, which, if you think of it in a simple example as a rectangle, if you have a rectangle with a length and a width, if you divide by that length, what's left? You get the width. So what we're doing here is we're finding the whole area, and then we're dividing by the width to kind of even it out and say, this is where my average value is for this function. All right, and we're going to do an example of that on the next board. All right, so for my last example here in section 3, I want to find the average value of f of x equal to the square root of 9 minus x squared on the interval -3 to +3. Now, f of x equal to the square root of 9 minus x squared is the equation for a semicircle. And it's a semicircle that goes from -3 to +3 very conveniently and sits right on the x-axis. So it's only the semicircle because it's just a positive square root. We wouldn't even have a function that had a plus or minus. Anyway, so I can find the area of that just fine. It's just going to be 1/2, because it's a semicircle, times pi r squared being the formula for the area of a circle. And if I plug in my 3, because that's my radius, I get that the area of that semicircle is 14.14. So its average value, or its mean, is 1 over 3 minus -3, right, the length of my interval. And that's 1 over 6 times the 14.14, which gives us an average value of 2.36. And so there you go. That's finding an average value. So we're going to, in this section, you're going to spend a lot of time working with areas, and that's perfectly acceptable. In the next section, we're going to go to some more generic functions where we're going to have to think a little bit differently. So come back for the next section and it'll be a lot of fun.